Hello, everyone. Welcome, and thanks for joining in today to my brief presentation at this symposium. My name is Feliks Nüske. I'm a postdoctoral researcher at Paderborn University in Germany. The topic of my presentation today is data-driven analysis of stochastic dynamical systems, and I will present on a method called Gedmd. Gedmd is a modification of the extended dynamic mode decomposition algorithm for the purpose of approximating the generator of a stochastic dynamical system. My presentation has two parts. In the first part, I will outline the basic method for the purpose of generator approximation. And in the second part, I will show how these models can be used to perform model reduction on a stochastic system. So let's set the stage. We consider a system xt, that's a time-dependent process, which is driven by a stochastic differential equation, or SDE. So that means that the instantaneous change in time of the system is controlled by two components. The first is a deterministic forcing driven by a vector field B that's called the drift. So the first part is what we would also encounter in the case of an ODE. But on top of that, there is also a stochastic forcing driven by the Brownian motion BT. And at each point in space and time, the intensity of the stochastic forcing is controlled by a matrix sigma, which is usually called the noise matrix or the diffusion matrix. As an example, which is quite familiar, which is often used in physics applications, I have listed the overdamped Langevin process. Here, the drift vector field is the negative gradient field of a scalar function v, called the potential energy. So the deterministic forcing is just driving the system downhill, but the system is also subject to the stochastic forcing in form of the Brownian motion, and the intensity of the stochastic forcing is controlled by a constant, which in turn is related to the temperature of the system. Next, let me introduce the generator. The generator of an SDE is a second-order differential operator, which I denote by L, and it acts on a function psi by multiplying the gradient of this function by the drift vector field, and we multiply the Hessian matrix, or matrix of second derivatives of that function, by the covariance matrix A. So A is directly related to the noise matrix sigma by A equals sigma times sigma transposed. Going back to the overdamped Langevin process from the previous slide, the generator takes the following shape. L is equal to minus the negative gradient of v times the gradient of the function, and the second order term just collapses into a constant times the familiar Laplacian operator. Now, what is the relation between the generator and the stochastic process itself? And this relation is the following. The generator L basically contains all information about the statistics of the process. In more detail, we have the following result, which is a standard result in stochastic analysis. For a regular function f, we consider a function which is a function of two arguments, time and space. And the value of this function v of t and x is the expectation value of our function f after letting the dynamics of the process evolve over time t, starting initially from x. So this function describes the time evolution of the expectation value of this function f as the dynamics progress in time. And then it can be shown that this function v of t and x actually satisfies a PDE, a generalized heat equation, which is just the time derivative of the function v at all times and all positions x is equal to the action of the generator on the spatial component of v of t and x. So here's the relation between the action of this second order differential operator L and the statistical information about the process xt. Okay, so since L is a differential operator, so an infinite dimensional object, if we want to work with this object, we usually have to compute a finite dimensional approximation. That should be a matrix approximation. And the standard way to do this is to compute a best approximation of this generator on a finite dimensional subspace. So more detail, let us fix the probability measure mu, which will in most cases be the invariant measure of the process xt, assuming it exists. And then we fix a finite dimensional space W spanned by some basis functions psi I, which should be a subspace of the Hilbert space L2 mu. So the regular L2 space was weighted by the probability measure mu. And then it follows from standard Hilbert space theory that the best matrix approximation to L on the space W is the following matrix, also denoted by L, and it's a product of the inverse of a mass matrix G times a stiffness matrix A. So the elements of G are just inner products in L2 mu between any two basis functions, psi I and psi j, and the entries of the stiffness matrix A are given by basically the sandwich between any basis function psi I and the action of L to another function psi j. And all of these inner products again are weighted by the probability measure mu that we have selected in the first place. Now, in order to make use of this in a data-driven context, what we have to do is we have to realize that all of the entries of these two matrices, G and A, can be read as expectation values with respect to the probability measure mu. For example, any entry Gij of the mass matrix can be seen as the expectation value of the product psi I times psi j with respect to mu. But as a consequence, if we have data sampling the measure mu, or at least approximately sampling the measure mu at our disposal, we can just replace this usually high dimensional and complex integral with respect to the measure mu by a simple time average of the product psi I times psi j across the data set sampling from mu that we have at our availability. And now all that's left to realize is that if we know the coefficients of the SDE, so if we know the drift vector field and the diffusion matrix field, then we can also evaluate the action of the generator L on any basis function at any specific point in space. In other words, we can apply the same reasoning to calculate the matrix A, to approximate the matrix A from a sample of the probability measure mu, exploiting, again, let me stress this, exploiting the fact that L is a differential operator and hence its action is completely local. So this is already the gist of the method, which we call Gedmd. So let's assume we have a sample of points in our state space, which approximately sample the probability measure mu. Then we can just approximate G and A by simple time averages. And the way to do this, or the way to write this in a compact manner, is to define a matrix X, which simply contains the values of all basis functions at all data points, and another matrix Gx, which will contain the evaluation of L applied to any basis function evaluated at any data point. And then the empirical estimates for the matrices G and A, which we call G hat and A hat, can be calculated as 1 over m x times x transposed and 1 over m x times dx transposed, respectively. And let us note that the source of these data points, xm, is actually quite variable. For example, if we were able to directly sample the measure mu, then we could just draw these points independently. Usually that will not be the case in high dimensional settings, but here's where I think the real strength of the method comes into play. We can, if mu is the invariant measure of the stochastic differential equation, then we can just generate a long trajectory such that the points of this trajectory will actually sample the measure mu, and then the Birkhoff-ergodic theorem will guarantee that in the limit of infinitely long trajectories, we can also just use these trajectory points within the framework of Gedmd, and these empirical estimates will converge towards the true matrices G and A. So let us move on to the topic of model reduction. And let me first sketch the framework for model reduction we will use. And the idea is just to replace the high-dimensional SDE xt by another SDE zt, which is defined on a set of lower-dimensional reaction coordinates z. And these reaction coordinates are related to the original state space variables x by some function, by a coarse-graining mapping xi. And again, let me stress that we explicitly make the choice of modeling ZT as another SDE, so there are no memory effects taken into account. That is a modeling decision we just make for the purpose of this talk. In a little more detail, let X be the original high-dimensional state space and Z be the reduced state space. So X is collapsed into Z by the action of the coarse-graining function xi. And then the key tool we will need is the projection or averaging operator, which simply takes a function f on high-dimensional state space and converts it into a function pf on low-dimensional state space by evaluating the expectation of f across the level set of the coarse-graining function xi. So we just calculate the expectation of f subject to the fact that xi of x is equal to the point z. So in this way, we generate a new function of the reduced variables only. Then the key insight from these papers down here is that if we apply this projection operator P to the generator, and this is indeed a projection in the Hilbert space of square integrable functions that we talked about before, then we obtain another operator L xi, and L xi turns out to be, again, the generator of a stochastic differential equation, ZT, on the reduced space. And we can indeed calculate the new drift and the new diffusion on lower dimensional space by means of the projection operator, by means of the coarse-graining function, and by the original generator. Okay, so let's see how we can use Gedmd within this model reduction framework. And we start by setting out with, again, a finite dimensional space W spanned by functions psi k. And now we assume these functions psi k are actually functions of the lower dimensional set of variables. So they are functions on the reduced space Z. But clearly, we can also regard those functions as functions on full space just by a composition of these functions psi k with the coarse-graining function xi. In other words, psi k tilde, which is just defined as psi k composed with xi, is clearly now a function on the original state space x. And then the key result, which we stated in this proposition, was that if we have data sampling the original process, the original SDE xt, or the original invariant measure mu on high-dimensional state space, and we use this data within the context of Gedmd, and using the basis functions psi k tilde, so these composed basis functions, then the resulting matrix approximation actually converges to a Galerkin projection of the projected generator L xi. And note that if we apply Gedmd, which involves the full generator, to these functions psi k tilde, then we need to apply the chain rule to calculate all the derivatives which are involved. And I've just put down these expressions here in the middle of the slide. So this looks more complicated than it is, but it is really just application of the chain rule to calculate the action of the full generator onto these composed basis functions psi k tilde. So again, in summary, what we can do now is we can use data of the full process or data on high-dimensional state space. And if we know the coefficients of the original dynamics, so if we know the original drift and the original diffusion, then we can use these data together with a basis set supported on low-dimensional variables to calculate a matrix approximation to the generator of the resulting effective dynamics, of the resulting reduced dynamics. And note that we do not need to know or compute the exact coefficients of the reduced SDE in order to do that. And we also do not need to sample the reduced SDE on low-dimensional space. And this is useful for a number of reasons. So first of all, we can use a matrix approximation to the reduced generator in order to infer a number of properties. For example, we can actually use the model, the Gedmd model, to identify the coefficients of the reduced SDE in the first place. So if you want to know more about it, we've discussed a number of techniques to do so in this paper below. But we can also compute spectral properties, or at least approximate spectral properties of the reduced generator by just calculating eigenpairs of the resulting matrix approximation that we just obtained from Gedmd. In order to illustrate the usefulness of this last point, let me draw your attention to the following error estimate, which you can find in the preprint referenced down here. So for a reversible process, xt, we can compare the eigenvalues kappa I and eigenfunctions psi I of the original process, so of the full generator L, and the eigenvalues omega I and phi I of the projected generator Lxi. And then we find, first, this is a standard result, that there is a variational principle, so the projected eigenvalues will always overestimate the full eigenvalues. And in this paper, we also derived a relative error bound, where we were able to show that basically the relative error between projected and full eigenvalues is bounded by some prefactor terms, the projection error of the corresponding eigenfunction onto the space of lower dimensional functions. And the reason this is useful is the following. So if we have data of the full process available, then we've already seen that we can use Gedmd with a basis set supported on lower dimensional space to approximate these projected eigenvalues omega I. And now we can use the same data set, the data sampling the original process, to calculate these matrix approximations using different reaction coordinate, different choices of reaction coordinate psi. And the variational principle, or the error bound shown down here, they actually give us a way or a measure to compare the approximation quality resulting from different matrix approximations corresponding to different choices of the reaction coordinate psi. So without having to go to the length of setting up the reduced model and of actually simulating the reduced dynamics, we can compare different choices of reaction coordinate and therefore guide the search for a suitable reaction coordinate. All right, this was what I wanted to present today. Let me just conclude by thanking Stefan Kloos, Sebastian Peitz, Peter Koltai, and Cecilia Clementi for the collaboration on these projects. And I would also like to thank the organizers for setting up this beautiful online meeting. And finally, thank you all for your attention.